Okay. A very warm welcome to one and all listening to my video. I'm Kavan Mathi, studying final year in electrical and electronics engineering, and today we are going to see about a concept named commutation failure. So in this video, we are going to see about what is meant by a commutation process and what is meant by a commutation failure and what are all the costs and effects of the commutation failure and how to mitigate this commutation failure. So let's go into the video. So first, we just see what is mean by a commutation. A commutation can be said in two ways. In first way, in DC machines, we just say a commutation is a process in which we are converting an alternating current into a direct current using a commutator. So in a DC generator, the generated output will be an alternating current only. So for a DC generator, we need to convert that into a direct current. So we are just using a split ring to convert this alternating current. So the process of converting the alternating current into direct current using the commutator is called as the commutation process in DC machines. But in HVDC, it is somewhat different. So as per the book, what they are saying means the switching of current conduction from one of the thyristor valve to another in the same row of a converter bridge is referred to as the commutation. So let's see this in detail. So let's see this. I just explained this with an image. Sorry. So this is the image of a three-phase six pulse converter. So we are having a six thyristor 1, 3, 5 and 4, 6 and 2. So and the sequence of operation will be like so if we start from 6, the sequence of operation will be like a 6 1 1 2 2 3 3 4 4 5 and then 5 6 and again 6 1 and it will goes on. So let's take 1 2 as a starting sequence. So if 1 and 2 are in conduction, the other four thyristor will be in an off state. With these all are will be in a reverse bias condition. Just 1 and 2 will be in the forward bias condition. So when 1 and 2 will be in forward bias, the circuit will be like this. But just remove this center part, just assume the outer loop only. So the thyristor 1 and 2 will be in a forward bias condition. So after this 1 2 sequence gets finished, 2 3 sequence need to switch on. But before so for switching from 1 2 to 2 3, what is just changing, we are changing 1 with 3. That means the current through thyristor 1 will be reduced and the current through thyristor 3 will be increased at the same time. So what happens means we are when this operation, when 1 2 are in sequence and they are in operation, and if I am giving an triggering pulse to this thyristor 3, it gets triggered. So the this thyristor 3 will be in sorry um, sorry, this thyristor 3 will be in a forward bias condition. So the here if we see this, it will provide a reverse bias condition, a reverse bias condition to this thyristor 1, and it will make this thyristor 1 to be turned off, and when it gets completely turned off, thyristor 3 will take the control over this load current id, and after this after this thyristor T1 gets off, the current will be flowing from uh, thyristor 3 and will be entering thyristor 2. But before this before this 2 3 gets into operation, the output id will be controlled by both of this thyristor. The current through this thyristor 1 will be reduced and the current through the thyristor 3 will gets increased. Okay. So at this process of decreasing the thyristor 1 and increasing the thyristor 3 to shift from this sequence to this sequence is known as the commutation process. Okay. So let's see this. So these are the graph of the commutation. This black line is the output ID current from thyristor 1. After this thyristor, this is the line of thyristor 3, the output current of thyristor 3. So when this thyristor 3 gets triggered at this alpha, it will provide a reverse bias condition to the thyristor 1, and see, this will get reduced and it will get on. So the sequence will be changed after this time period. This time period between this increasing and decreasing currents is called as the commutating time period, and this process is called as the commutation. And the output voltage will be a potential difference between this UA and UB, and the resultant will be like a UBA. Okay, and the current will be like this. So this will happens for every sequence. It will happens between every sequence. If 1 to come into operation, 6 and 2 will be in commutation, and here 1 and 3 will be in commutation, here 2 and 4 will be in commutation, and this process goes on. Okay, let's see what is the commutation failure and when it occurs. So um, if this so for perfect commutation, here the gamma should be greater than or equal to 15 degrees. So if let's say this is 15 degree, if this is let's see from this equation, the beta is the sum of the mu plus gamma. This gamma is for the switching on time of complete switch on time for the thyristor 3. This gamma should always be greater than or equal to 15 degrees. If this is less than 15 degrees, then commutation failure occurs here, and I will say you why that happens. This mu is the switching on time of the thyristor 3, and beta is the sum of these two angles. Okay, so beta is the sum of mu plus gamma, and the condition I have said, this gamma minimum of the extinction angle gamma should be greater than or equal to 15 degrees. So if this is greater than or equal to 15 degrees, the the thyristor turn of time will be greater than the reverse thyristor turn of time will be greater than the turn of time, and the thyristor T1 gets properly switched off. But if this gamma is less than 15 degrees, what happens means this the reverse time of the thyristor TR will be less than the turn of time of the thyristor, and it doesn't switch off properly, and again it comes into operation, and the sequence will be like 1 2 3 again and again. So here the commutation failure happens. So at the place of 2 3 needs to happen, here also 1 2 3 will be in operation. So commutation doesn't the effect of this means it will provide a lot of it will induce um, heat to the circuits, and it gets affected. So these are the wall currents during the successful commutation, and these are the wall currents during the unsuccessful commutation. If the commutation failure occurs, the ID current will be like this, and it will not be uniform. Okay, uh, let's see. Sorry. So this is the graph of the commutation failure. If gamma is greater than 15 degree, 1 will get switched on properly and 3 will get switched on properly. But if it less than 15 degrees, this 1 will not switch on properly, and it will again comes into operation. I hope you are now clear with what is meant by a commutation and commutation failure. So now I'm going to explain the commutation failure in terms of theory. So what they are saying means commutation failure is the failure of an incoming value to take the control of the load current when commutation voltage reverses its polarity. So from the example we have said, so if 3 needs to take the control of the load current and the thyristor 1 should be gets off. But if the failure occurs, if the extinction angle is insufficient, what happens means the thyristor 1 again takes the control of the load current, and this leads to the commutation failure. Okay. So here they are saying about the effects, the wide occurrence of the commutation failure. They may occur due to the consequence of the voltage dips due to AC system faults or switching actions, mainly in inverter stations like that. So let's see this in detail in further slides. So what are all the causes of the commutation failure means the main three events that cause commutation failure are the decrease in the commutating voltage, a sudden increase in the direct current, and the third one is a hardware malfunctioning in the firing control. I will explain these three events in detail in this slide. So here they have said a sudden increase in the direct current. If we increase the direct current suddenly, what happens means this mu. What is mu? This turn on time. What is mu? This time. If this mu gets increased up to this, if this here, let's see this gamma is here at 15 degree. If this mu gets increased up to this angle, this 15 degree will be less. That means this gamma will be less. So they're saying that only if this mu gets increased, this gamma will be reduced. So from the equation, what we have said is beta is the sum of mu plus gamma, and gamma is equal to beta minus mu. And if this mu increases, gamma will be reduced. What I have said, the minimum gamma should be 15 degrees. But if it gets reduced, if it gets less than 15 degrees, the reverse turn of time will be less than the thyristor turn of time, and so the commutation failure occurs. And the first reason they are saying is a decrease in the commutation voltage. If there occurs a short circuit condition, and if there occurs a low AC side voltage, means if short circuit happens means the voltage will be reduced to zero. Okay. Mm. So if this voltage gets increased, that time also the mu gets increased, and this, so as the result, if mu gets increased, gamma will be reduced. At the time also the reverse thyristor time will get less than the circuit turn of time, and it will also cause commutation failure. And third one is the hardware malfunctioning in the fire control. That means if if the fault is from our side, if we are giving a mu for a if we are scheduling the mu for a long time, or if we are scheduling the gamma for a least time, if the mistake is made by us, then also it will cause a commutation failure. So I hope you all are clear with this three causes which may cause the commutation failure. And finally, just see what is the mitigation of the commutation failure, how to control or how to prevent this commutation failure means. So from the if you see, if we want to prevent something, we need to reduce the causes. So what are all the causes? The increase in ID, and the reduce in voltage due to short circuit, and the malfunction created by us if we schedule the time very low. So the how to prevent these three means, so from the third point, if we are scheduling this at a least time, we need to schedule the switching time prior to the scheduled time. So it can be avoided by so here they are saying us it can be avoided by temporarily increasing the commutation margin just before a planned switching action. This will mitigate against the commutation failures associated with the scheduled switching. After the schedule switching, the commutation margin is restored to its steady state value. So, in order to decrease the risk of the commutation failure, the steady state commutation margin is increased. The larger this margin, the more severe the disturbances can be without commutation failure. So, they are saying to, so what they are saying is, here is, so to maintain this margin lines, we can prevent this type of commutation failure. Okay, but if the failure occurs, if we create the failures, we can adjust it. But if occurs due to a circuit failure, and for replacing it and for uh, operating with the margin, the cost of equipment will be high and it will cause a higher loss. And thank you for your patient listening, my dear listeners. And if you have any queries, you can comment below. Hope you all are clear with this. And then also, if you are having any queries, just comment below. I'll just upload this video in my YouTube channel. Thank you.